Have you ever wondered how scientists and engineers design the chips that power our smartphones, computers, and other electronics? Or how they create the materials used in LED lights? At the heart of these scientific breakthroughs lies a deep understanding of a material's energy states, knowledge that reveals which optical transitions occur and how to control them with precision. One powerful way to achieve this is by modeling the energy states of a solid using finite quantum potential wells. In this video, we'll start with the fundamentals and guide you through how this technique is driving innovation in electronics and quantum computing. Let's begin by defining the finite potential well problem. This is when a particle, like an electron, is confined to a box with finite potential walls. Classically, if the total energy of the particle is less than the potential energy barrier of the walls, it can't be found outside of the box. Think about a ball rolling across a valley. If it starts at a height below the top of the next peak, it won't have enough energy to continue forward. However, in quantum mechanics, there is a certain probability that the particle can be found outside of this box due to the quantum tunneling effect. The finite potential well can be described as follows, where L is the well length and V naught is the well depth. Note how the potential is equal to V naught outside of the well and equal to 0 inside of the well. The time-independent Schrodinger, or TISE, equation helps us to understand the quantum state of a particle, as described by the wave function psi. The wave function tells us where the particle, like an electron, is most likely to be found. For example, it can show us how close the electron is to the nucleus of the atom. By solving this equation, we also find the specific energy levels, E, that the particle is allowed to have. These energy levels are discrete, or quantized, meaning that the particle can only have certain fixed values of energy, not just any value. This is contrary to classical mechanics, which teaches that energy is a continuous spectrum. To solve for these energy states E, we begin by simplifying the second-order differential equation for when the particle is inside the well, or V naught equals to 0, and outside of the well, or when V naught is not equal to 0. Second, we enforce some boundary conditions which pretty much state that the wave function psi should behave as an oscillatory wave within the potential well, and exponentially decay when outside of the potential well. After a little bit of calculus and algebra, we arrive at the following equations, which must be solved simultaneously to determine E. This is usually solved graphically, as shown. The way we just determined the energy state, E, is called an analytical solution. For more complex potentials, it is quite difficult or impossible to solve analytically. Thus, we need to stick to numerical methods. Let's begin by discretizing the TISE, as shown. The naive way to solve this equation would be to guess values of E until the wave function tail exponentially decays to 0 outside of the potential well. When we use guess E equals 5, we get the following wave function. Note how it instead blows up exponentially in the forbidden region. After many such guesses, we iteratively converge on E equals 3.413571 for the first energy state, as shown by the smooth wave function, which exponentially decays outside of the potential well. This method is known as the shooting method, as we are taking shots in the dark when guessing for values of E. Thus, we need to develop a more robust method. To begin, we assume that the wave function is a linear combination of basis functions, phi of n, where we need to solve for coefficients c of n. A good approximation for these basis functions phi of n are sinusoids, as they are continuous, differentiable, and oscillatory. We can then substitute the wave function approximation into the time-independent Schrodinger equation to get the following expression. After applying some physics and math tricks, we can simplify to the following expression, which can actually be written in matrix form as shown, where H is the sum of the kinetic energy, H naught, and potential energy, delta V, given by the following definition. We define energy E as discrete energy levels, N, as follows. Once we solve for C of N using linear algebra, we can plug it back into the following equation to finally solve for the wave function. Note how in figure A we obtained the ground state wave function as solved previously with the shooting method. We find that the corresponding energy E is nearly identical to that found with the shooting method. In figure B, we take it one step further and solve for the wave function at the first excited state, which means that there's one more oscillation compared to the ground state. We find that there is one node, or a region of the wave function where the probability of finding the particle is 0, which is expected. In a solid, atoms are arranged in a periodic lattice. Each atom acts as a potential well for electrons. Thus, we can expand the single finite potential well to many of such wells so that we can study how electrons move through the lattice, leading to fundamental concepts in solid-state physics. First, we define 10 equally spaced, periodic, finite potential wells as shown. Then, we can use the matrix method we just derived to solve for the probability density, equal to the wave function squared, representing the first 4 energy states of this system. The first thing we note is that the ground state looks similar to that of the single finite potential well. This is roughly a Gaussian distribution, which states that the particle is statistically likely to reside near the center of the well, with decreasing probabilities towards the walls. The first excited state is more of a bimodal distribution, with particles residing near half of the distance to the centers. All of these energy states can be interpreted as constructive and destructive linear combinations of atomic orbitals. This is known as the LCAO molecular orbital theory. In solids with numerous finite potential wells, atomic orbitals hybridize to form molecular orbitals with varying energies. Due to the proximity of many such atoms, these orbitals create continuous energy bands. The Pauli exclusion principle restricts each orbital to a maximum of 2 electrons, and the bands are filled starting from the lowest energy levels. We highlight this effect by plotting the energies associated with each of these linear combinations, as shown below. Note how the energy states in the 10 potential well system are so close that they start to form the characteristic bands of electrons in solids. It turns out that the LCAO approach, combined with these multi-finite potential wells, can be utilized by computational chemists for low-cost, semi-empirical calculations of material electronic properties, like band structure. This is especially important for systems with greater than 10,000 atoms, for which we cannot use density functional theory to account for complete interactions. For smaller systems, however, LCAO is not very accurate, as the potentials are not actually of rectangular well shape, but rather asymmetric, like Leonard-Jones. Nevertheless, it is an important stepping stone for more accurate and widely used methods in first principles methods like DFT, which approximate the single particle energies. In this video, we review the numerical and analytical solutions for the time-independent Schrödinger's equation for single and multiple finite quantum potential systems. If this were to be done in the future, maybe better generalizations for periodic potential behavior can be made, such as the Bloch's theorem. Second, different, more realistic electronic potentials like Leonard-Jones or Morse can be explored to evaluate the effect they have on the results. Lastly, more computationally efficient techniques can be utilized for solvers, such as the Thomas algorithm for the sparse tridiagonal matrix and domain decomposition methods for the boundary value partial differential equation problems. The PDEs and matrix problems were found to take a lot of time to solve and scaled poorly, especially for multiple finite potential well systems. Both the code in Mathematica and paper, which explains all of the numerical methods used in detail, are in the description below. Sorry for all the math in this video. This is just the nature of explaining quantum mechanics topics. Please make sure to like, share, and subscribe to keep updated, as I have some videos planned on fluid dynamics and machine learning, which I will make shortly. If you are able to, please comment what topics you would like to see, or improvements that I can make to my videos. As always, thank you.